Hello everyone. In this video, I want to present LiMe, a Python package we made to measure lines in astronomical spectra. You can read about all its features in the LiMe publication and its documentation by clicking on the links on the screen. In this first video, I would like to provide an introduction on how to use LiMe to analyze long-slit spectra. If you have any doubt, please leave a comment here or open an issue at the library GitHub. On the video description, you can find the links for these different sections. And finally, remember to increase the YouTube resolution and to activate the captions to better follow the commands. Okay, let's start by installing LiME using pip. We just need to run this command, pip install LiME stable, and it should also install all the required dependencies, which you can find in the documentation. Very good. We are going to launch the IPython shell to run the commands. LiME, however, should run on any IDE you use. You can find on the documentation the tutorials as Python script and as Jupyter notebooks as well, in the GitHub's examples folder. Let's start by importing LiME. Since in this screen the default plots may look a bit small, we're going to increase the resolution. You can read more on how to personalize LiME plots on the documentation, and at this point we need to create an observable variable. LiME has a composite software design. At the highest level, we define observation variables, which contain the scientific data. From these objects, we can access the .fit, .plot, and .check attributes, which provide the fitting, plotting, and interactive functions respectively. At the current time, LiME can create observations directly from fits files from certain instruments. If your instrument is not currently supported, please post a comment and I will try to add it as soon as possible. Or in the documentation, you can read more on how to use Python to read fits files. In this case, we're going to analyze the SLOAN observation of the galaxy SO 579. So to load this spectrum, we're going to run this command. Normally, we would need to specify the object redshift and possibly the normalization for the flags. However, the SLOAN.fits header file already includes the redshift. So to check the characteristic of this spectrum, you can access its variables. You can see that the normalization is 1, but since these flags units already have an scale, this is okay. You can plot the spectrum by running this command, .plot.spectrum. At this point, we can start measuring lines. With line, you have the option to introduce the wavelength in the res frame, and line will try to find it on its bands database. For example, if we run the command .fit.bands and now plot the results, you can see it successfully recognizes each bit. However, this is not the best way, since it can cause issues with identification or there could be a mismatch with the unit. Instead, in line, we propose a notation based on the particle and transition and its units. This notation can also be used to describe the transition properties and profile type. You can read more about it on the manuscript and the documentation. For example, we can measure the nebular O3 line using the previous command. And now if we plot the result, you can see the fit. However, it is not very good. There is a wider component which is not being measured. Moreover, you may also want to measure multiple lines in one go. To do that, we need two things. The first one is a table with the target lines and their bands. We are going to adjust the default lines bands database using this command. The only attribute is the output text file where we're going to store the selection. In this grid plot, by default, all the bands are deactivated. You can right-click on the individual plots to confirm the presence of lines. The name of the line is on the top of the plot. Moreover, you can adjust the size of the bands. LiME uses a leak indexes band style where you have 3 bands, 1 for the line location and 2 for the adjacent continuum. It is important that these band edges wavelengths are sorted from lower to higher values in the res frame. To adjust the continuum bands, make sure that one click is inside the original blue or red bands. For the line band itself, make sure that the initial click is within the current W2, W5 range. Finally, you can use the middle mouse button to adjust the line label suffix. You can see this taking effect on the title of the subfeed. In LiME, we consider 3 line types regarding the number of transitions. For single lines, the default, you don't need the suffix. If you have a blended line, such as the case of H-alpha and the nitrogen doublet, you need to include the blended suffix so LiME can fit multiple profiles. You also have the option to declare merge lines. These are lines where we know that there are several transitions, but we may not have the resolution to fit multiple components. However, we may still want to include the component names for the output measuring files, for example, to apply the appropriate photonization models. So let's continue adjusting our selections. And once we are happy, we can close this window. It is useful to remember that if we run this command again, we are still comparing with the default database, but our results are being measured. Okay, that was the first input. The second one is the configuration for our fittings. In this case, you should also use an external file. In LiMe, we use toml configuration files. You can read more about this standard at this link, but over here we have an example. This file contains pairs of keys and values organized by sections which use square brackets. It is important to remember that LiMe will read sections which include the line fitting suffix. In the default line fitting section, we have the components for the blended and merged lines. And we are also specifying the properties of the fittings. For example, for the O3 line, we want to consider its wide component as well as the weak helium line. We are copying its kinematics from the 4959 Astro line for both the narrow and wide components using the kinect command. For the helium line, for example, we are placing boundary on the centroid for its Gaussian profile. Similarly, for H alpha, we are setting its wide component sigma to be at least twice the value of the narrow component. Also, we are fixing the amplitude ratio of the nitrogen duplet to match the theoretical emissivity ratio between these lines. Also, we are imposing the kinematics of the most intense nitrogen 2 line on the weaker one. Unlike in the case of the O3 lines, since both N2 lines are being measured at the same time, their kinematics will vary during the fitting. They are just tied together. There are more options to personalize your fittings, which you can find on the documentation. We can now run this configuration with this command. And here we introduce in the addresses of the bands table and the fitting configuration. And if we press enter, that was it. You can see the results by running the plot command. And if we zoom over H alpha, if you have installed npleer cursors and you click on the profiles, you can get these pop-ups. You can see that the nitrogen doublet has the same velocity dispersion and radial velocity in the line of sight, and the Gaussian fluxes ratio is almost 3, as requested. We can also plot the results as a grid, running the command .plot.grid. Finally, you can also save the results into multiple files using the save frame command. The first one saves the results as a text file, the second within an extension of a .fits file, and this one will only save the integrated and profile fluxes as a PDF, which should be around here. Independently of the output file type, you should have the line version, the redshift, the units, and if you included it, the observation name. At this point, I advise you to check the first, second, and third tutorials on the documentation, where we go over these steps at a slower pace. However, before finishing, I would like to share a few tips to better handle a large number of long-slit spectra. In the case you have many observations and you don't have the time to confirm the presence on each individual file, you can configure the peak intensity threshold detection algorithm to do this for you from the configuration file. To test the best settings, you can use these two commands. The first one is to fit the continuum with the .fit continuum command. The first attribute provides the degree list for the continuum polynomial, and the second, the threshold for the pixels above the continuum standard deviation. Since we did not specify an absorption threshold, it will use the same limits. Finally, we're going to request a plot for each iteration. So, in this first iteration, you can see the 3-degree polynomial with the fit continuum and the rejected pixels. This is the second iteration with new rejection and a lower intensity threshold. And this is the last one. You can review the continuum fitting using this command, where the include continuum parameter is true. The second step is the actual thresholding algorithm using this command. The first attribute is the bands data frame we adjusted before, and the second is the intensity threshold for the continuum fit and the standard deviation that we calculated before. The last attribute requests a plot with the results. You can see that overall we have a good detection, although we are missing some lines. We are currently working to apply new techniques to make this process easier, but for the time being you need to play around with the continuum and line detection functions parameters. At any point, you can review the bands from a given data frame using the plot.spectrum command, where we are just adding the matched bands data frame. This can help you to confirm the presence of lines and the size of the bands. The second tip is to use several configuration levels for your fittings. Over here, we have a new configuration file. It is very similar to the previous one. The main difference is that the configuration is in two sections. The first one is the default line fitting, where we have the merge lines and the blended lines components, as well as the configuration for the continuum fitting and the line detection algorithm. The second is the SOC 579 line fitting section, which contains the configuration for this galaxy. Finally, since we are assuming that we are measuring many objects, let's load the bands and configuration files in advance. The load frame command will read the file as a pandas data frame, while the load configuration command will read the toml file as a dictionary of dictionaries. As we did before, we're going to use the .fit.frame command. The new attributes have two effects. The first one is that the default line fitting configuration is going to be updated with the one from SOC 579. Currently, the only way this works is that the repeated entries are replaced with the new ones, and the missing ones are added. And the second new behavior is that the fit.continuum and line detection commands will be run in advance, and only the positive detections will be measured. So let's run it. And that's it. Using this workflow, it should be easier to organize your analysis for large datasets. You can also try to have different configuration files for different types of observations. So this is all I wanted to show you for now. In the next video, we will use LiMe for the analysis of IFU datasets. You can, however, find all the steps on the 4th, 5th, and 6th tutorials, as well as the LiMe paper. I hope this helped you, and please feel free to drop your issues and comments here or on the GitHub page. Thank you for your time.